Hello, in this tutorial, we'll be doing a simple linear regression analysis on Microsoft Excel. At the end of this tutorial, we would have been able to learn the process of regression analysis on Excel, understand the values or results we get from the process, and be able to interpret the relevance of these values to you and for whatever process you're using it for. What is regression analysis? Regression analysis is the process of building or developing or training a model that would enable us predict our dependent variable from new values of our independent variable. An independent variable is a variable that can be used to change or control or used to predict our dependent variable. While our dependent variable is the variable that we want to measure or is being calculated. For instance, if we are using the age of individuals to predict their current financial value, then age is our independent variable and the financial value is our dependent variable. Okay, so independent variable is our control element and dependent variable is our measured or measurable element. We'll be using a simple sample data set, which I'll provide link to download in the description below. So please make sure you download and follow through as we go through this process. And don't forget to like and subscribe and share with someone. So the data we have here is a data that has the income of individuals and their happiness index. So with the income, we would be learning the relationship between income and happiness of individuals. At the end of this tutorial, we will be hoping to have developed a model that could help us to predict values of our happiness index from our independent variable income. Remember again, your independent variable is your variable that can be changed to control your dependent variable, while your dependent variable is your variable that is being measured or calculated. Another example that we can give is the number of sugar cubes and the taste of your tea. So the number of sugar cubes is my control element. If I increase the number of sugar cubes, I expect that the sweetness of my tea will increase. So my independent variable is my number of sugar cubes, while my dependent variable is the taste or the sweetness of my tea. I hope that helps us to understand. All right, so we have our data set, our independent variable X and our dependent variable Y. So on your Microsoft Excel, you would want to go to your data tab and you would look for an icon or a name here, a button here for data analysis. Now, if you don't have that available on your system, then you would have to do this with me. So go to File, go to Options, select Add-ins because it's a data analysis add-in that is not available yet. So you can see it here. Now, if you want to add any add-in to your Microsoft Excel, you check for what type that particular one is. And this is an Excel add-in. So you make sure what you have selected here is an Excel add-in. And then you select Go. And I want Analysis Toolpack, which is what contains our data analysis. And we select OK. If you've done that well, you would have seen that the data analysis now appears here. So if I select data analysis, I have different statistical analysis that I could perform, statistical measure. But so we don't spend so much time on every other thing, we are doing regression analysis in this particular problem. So we select regression and we select OK. So I'm going to try to be a bit fast with the process because we don't want to spend all our time on this. Now input your Y range, which is your value to be predicted, your dependent variable. I want to start from the first. Okay, so if I select the first cell, Control Shift down, which is including my label. So I have 498 data points. While for my X axis, I'm selecting for my X range, which is my independent variable, I'm selecting all. Now, because I included my headers in my selection, I would have to ensure that I tell the regression window or the regression solver that I have included labels. Okay? Otherwise, it's going to flag off an error. Now, for the sake of, being clear, you can put your output range somewhere else. Okay? You can put your output range here on this particular sheet, just so we are seeing everything, or you can add it to a new sheet or to a new workbook. Now, you can choose residuals, so it's going to show you residual. You can also select residual plot. You can also select line fit plot. For the sake of this analysis, these are the things we are going to be working with. Okay, so simply that, and Excel has calculated has done the regression problem for us. So that's the process of performing regression in Excel. Very simple, right? So I would explain a thing or two. Now, the problem we are solving here is a simple linear problem. It's a simple linear problem, and it's containing just two variables, just one independent variable and one dependent variable. But there are several things that this process we've done can tell us. Number one is these plots that we have here can tell us if our data is a linear regression kind of analysis. Is the relationship between X and Y a linear relationship? Okay, will it follow the formula Y equal to bx plus a, or is it not in a linear relationship? Let me attempt to explain what that means. If I add 1 cube of sugar to a cup of tea example, I expect that the taste of sugar is going to increase by a certain measure. If I double the cube of sugar, I expect that the influence of 1 cube of sugar in the taste of my tea should at least or around a double of what it was before. If I add 3 cubes of sugar, I'm expecting that the taste that was increased for 1 cube of sugar should increase by at least 3 times or around 3 times what it would have done for 1. Such a relationship is linear. Okay? But when you have that 1 cube of sugar is added to your tea and it increases by this measure, you add another cube, it doesn't follow the same pattern, probably has something much more larger, which can still be telling us about linearity, and then we add another one, and instead of it to increase by an average same amount, you have somewhat of a much larger increase. It means that the influence of your independent variable, your control element, is not linear with your dependent variable. Now, from our residual plot, you can be able to say that an independent variable is linearly related with a dependent variable by seeing the position of the residuals in a plot against residual against income. Let me explain what residuals are. The residuals are the differences between each observation and the predicted value. So you can see a residual output plot which was added here, and look at this. This is the predicted value of happiness on the model, based on the model that Excel has built for us, and this is the value of the residual. This is the original value that it was, right? So based on 3.8626, our model is predicting 2.96152, which is different from this, and the difference is minus 0.6470, which is our residual. So your residual is the difference between your predicted dependent variable and what the original dependent variable. Okay, so if the residuals are scattered around the 0 axis, around 0 on your x-axis, you can say that your data is linearly related. So it's a linear regression problem. If you have something like a curve, then it's looking towards quadratic and higher powers of regression. Now, let us head back to the values. I would also explain this line of fit. Okay, let me do that for the line of fit before we proceed. Let me just change the position of our legend to be top. And let's make this a bit bigger. Okay, so our line of fit plot is a plot of our independent variable against our dependent variable, and a line of fit is built or is drawn that can be used to predict what the values of our dependent variable will be from our independent variable. So the line of fit is used to somewhat represent that relationship. Now, the definition of this line of fit is what our linear regression, our regression model will have given to us, okay, which we'll soon see shortly. So, however, with this value, so this straight line that you have here, which is a line of fit, is a plot of our predicted happiness, okay, which is this, which are these. It should give us a straight line because it's a linear plot, okay, because it's a linear plot. So if I have an income value of 6, from this plot, if I trace that value to my y-axis, which is happiness, the value of 6 from this line is going to give me a predicted happiness of about 4.4 something or so. With that line of fit now, which is defined by our model, we can now predict new values of happiness from our income. All right, let us come to our values. We'll come back to these plots. The first thing we have here is our multiple R value. Which tells us the relationship between our income and our happiness as per the correlation. It tells us the correlation of happiness and income. Is there a strong relationship between income and happiness? Okay, if the value is greater than, so the value of our correlation is usually between -1 and 1. If the value is tending towards +1, is showing a strong positive relationship, If it is reducing, it's showing a negative relationship. So we are having a strong positive correlation coefficient here, which tells us that an increase in the income will reflect an increase in the happiness index. That's what this value means here. So that's the relevance of a strong positive multiple R or correlation coefficient value. So maybe you are doing a correlation in your business between customer retention and profits made. If your R is showing a strong positive value from 0.5 and tending towards 1, it means that there is a strong relationship, positive relationship between your customer retention and your profit. Okay. R square is a value that is used to denote how accurate our prediction was. And it's usually between 0 to 1. The greater it is, or the closer it is to 1, the more strongly we can affirm that our predictions are accurate, or we can trust the model more. Okay, so it shows a strong relationship in prediction. Okay, having about 75% here, we can say that our model is predicting strongly. Okay, and it also shows that it is accounting for a lot of variation. The model accounts for a lot of variation in the data set. For instance, here that you have 4.979 for your income, you have about 3.4 happiness. And when you have 4.92, which is still close, you have about 4.5, which is quite a big distance. But our model accounts for this variability, meaning that it can predict better, because you can see that the R square value is quite high. So if you're having a low R square value, it means your model is not doing so well in predicting your dependent variable. Your adjusted R square is also a metric of measurement. It's just an adjusted value of R squared based on the number of predictor rows that we're given. Okay, excuse me. All right. Standard error shows on an average, how variating is each value from the predicted from the original value. On an average, how variated is your predicted value from the average, or the original value rather. Okay, so having 0.71 means that on an average, what we predict is only different from our original value from about 0.71, which is actually a good result. Okay, if you were having a value of 2 points or 1 point, it means that on an average the prediction was not so good. It was predicting, for instance, where you would have 2.3 from an income of 3.8, it will be predicting something like 4.3. I don't know if that makes sense. All right. Also, Excel's data analysis regression does analysis of variance for you, which at the end of the day will be able to tell you your significance F value. It will tell you your sum of squares and your mean square, which in all are just trying to tell you how good is your predictor variable against your independent variable. Okay, so I have it, just written down here so I don't have to memorize everything. So when we have a large value of F, it shows that it is a good fit. Okay, I would explain this more, especially this significance F value, right? If you had checked when we were doing the data analysis part, or if you have an experience in statistics, there's what we call our alpha value, and there's what we call our significance level. Usually our significance level is 95%, which means that we would accept anything that is greater or an f value that is less than 0.05. Okay, we'll accept only an significance f value that is less than 0.05 because we are taking 95% significance. So 95% of our data is good. So if we have this value, this is times 10 to minus 151, it means that our model is very, 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 very good in predicting what our values are, which it means that it is accepted. Okay, we also have main regression results, which are these two. Remember that the issue of regression analysis, or the process of regression analysis, tends to produce a formula that will be of the form y equal to ax plus b, where x is your independent variable, y is your dependent variable. Your a is your gradient from your slope, from this slope of line of good fit, while your b would be your intercept. If you trace this line, your intercept on your y-axis. So stay with me. If you look at the b value, which is your intercept on your y-axis, you can see the value here as 0.2. And that 0.2, like I'm trying to say, is if you trace this line further down, you can see it is heading towards 0.2. So that's your intercept on your y-axis. So in this particular example we are doing, RB would have been 0.2. So would have had 0.2. So that's a 0.2 thereabout. Okay. While our coefficient of our x, which is our gradient of our slope, is 0.71. Okay, 0.71, which is the slope of this. So you may not be a statistics student or a math student, okay, but we are saying that the movement of this line is following, has that weight of 0.7. Okay, has that weight of 0.7, and because it is positive, it is heading in this direction. In this direction. So it's heading like this. Okay? Depending on how you see it. So it's heading in this direction. Alright? So our A is this income coefficient, which is 0.7. So our model will look like y equal to 0.71 x plus 0.2. This is what our model is telling us, that the relationship between our happiness index and our income can be predicted with this formula. Okay, as we'll see shortly. So let's say that we want to do that. Okay, we want to use this tool now to develop that formula, and we want to predict somebody having an income of 3. So let's say we have someone that has an income of 3, and we want to calculate what his happiness index will be. Okay, so we say the formula will be equal to, our model will be equal to 0.71, which is this coefficient of x, times what your income value is, plus the value of your intercept, which is this. Oh, okay, sorry, I'm still in my head. So you cannot use bracket like that. All right, so it's telling us for someone that has an income of 3 that our model will predict a happiness value of about 2.345. Now, if you have built a model like this, you will now be able to predict new values. So if you have a value of 6, it's going to have an happiness index of about 4.7. Now, if we check the range of our values, let's add filters and we check the range of our values, and we can see our maximum values around 7. So let's say someone has an income of 8, which is not in the data that we have. Because we built a model, right, based on this organization's rating of income and happiness index, we can predict that this person's happiness will be close to 6. And if we check, of course, I will soon explain why we have this lower and upper 95%. You have around 6.8 maximum. If you filter, you will see what values are there. Now, I would explain why we are having certain values that are looking bigger based on the formula. Okay, I'll explain that briefly. But our model can be able to predict that this is what our value will be. Now, we have standard error, which shows us how our values are varying from the normal. Shows smaller values indicate more precise estimates. So that's what I noted down here. That smaller values of standard error indicates more precise estimate. So the smaller this value, it means the more accurate the estimation is. All right. Another significant thing we can see here is our p-value, which is this significance value, significance f here, but in regression we'll call it our p-value. And we say as long as this value is less than 5%, which is 0.05, it means that we can accept the result of this analysis because it represents 95% of our data, right? It fits for 95% of our data. I hope that makes sense to someone. Okay? So if you have this value greater than 0.05, then we would have had to complain about our income predictor. Also, our intercept p-value was less than 0.05, so we can say it still best represents 95% of our data. If you have it greater than that, then you may have to, work a bit around your model because it may not be a linear problem, or you will need more sample of your data for it to predict more accurately. All right. Finally, before we move on, we have our lower 95% and our upper 95%. These are bounds with which we want to say that our model can be. So we are saying that our model prediction of 0.71 for our value of A, the maximum value that meets our 95% is 0.75, while the minimum value is 0.67. Okay? But this is the value that best represents. What this means is that there are certain values within our data that would have been predicted better with this value, but this value will not capture more values accurately than this value. So, for instance, if I write a model with equal to this times a value of x again, and I do plus, and let me use this value of intercept, and I enter. So we can see that we are having an increased value for 8. Okay, so that's why we have that upper 95%. There were values within this data that were best predicted with this than with this, but this predicted more on our line of fit than this. I hope that is clear to someone. Okay, so when we had values that were 6.8 and 6 point all that, okay, remember we have errors or little errors in our data, because you're having residuals. It was not accurately predicting every value, right? Because there are times when the value of the residual, so these are the values of our residuals. Okay, look at our residual plot here again. These are the values of our residuals. There are times when the values of our residual was this great, that is over value of 2 greater than what the actual value was. Okay, so if my model is predicting 8, or let me use a value that is here, let's say let this be equal to this, okay, which is this value here. So the difference between my predicted value and the actual value, what it should have been, is my residual, and it's a negative, so it will be minus, it will be on this downside. All right, I don't know if that makes sense. It will be on this downside, while if it was positive, it would have been on this upper side. Okay, so it means that my prediction was below by 0.64, while in this case where I have a positive, it was above by 0.88. Okay, so look at this particular value where I used an upper 95% to predict. It is telling us that the value should have been 3.276. So that's the reason why we cannot go with this value, because let's predict. Let's also see what the difference in residual would have been. So let this be equal to this minus the actual value, which is this. Okay, and I don't want this to change while I go down. So this would be the value of my so sorry, it's supposed to be this predictor minus this actual minus predicted, rather. Okay, all right, so this gave me a residual or a bias of minus 0.6, while this gave me a bias of minus 0.96. Now, you would not want a model that will be giving you larger biases or larger errors. If you do, your R-squared value would reduce and your standard error value is going to be increasing, because it is variating more and more from the predictions, from the original values. Your predictions are variating more and more from the original values. Okay, so at the end of your prediction, or at the end of your regression model, this line of it has told you that there's a linear relationship between your income and your happiness. Okay, that they are more linearly related, and then you've been able to build or develop a model that can be able to predict new values of happiness within these upper and lower ranges. Okay, so this upper range, okay, I should have done that better. So let me do this. Let me move these guys. Okay. Let's have this upper value here. Okay, it doesn't want to lose that content. Okay, that's fine. So let me also do for the lower range. Okay, so let me say equal to, this is our lower, times the value of our x, which is our income, plus our lower 95%. So this is what it would have given us if we use our lower 95%. We are saying that we have developed a model that will always be within, will give us predicted values within the upper and the lower range. Okay? So with this model, we can be more bold to predict what the happiness of our individuals are with 95% significance, right? With 95% confidence level, rather. With 95% confidence level. That if I have somebody's income at 5, we have 95% confidence that his happiness index is going to be around 3.77. We also have that the upper bound of our prediction, the upper bound of our confidence level is saying that at most, his happiness index is going to be 4.1. At least his happiness index is going to be 1.9. Okay, so that's for regression analysis. So you've been able to see if a data is linearly related from this residual plot, and this is something we also do a lot in regression analysis in Python. I'm also a data scientist, so we do several model training machine languages where we are trying to develop and train a model to be able to predict a dependent variable, right? From our train data, we'll test on our test data and measure our metric of accuracy. Okay, so a residual plot would help you to check the linearity of your data, so you can proceed to say that it is a linearly related data. If this plot is not scattered randomly around your x zero axis, your x equal to 0 axis, your y equal to 0 axis, if it's not randomly scattered around it, then your data is not linearly related. So y equal to ax plus b will not work, will not represent your data, right? You can only use y equal to ax plus b when it is linearly related. Secondly, if you see a recognizable pattern in your residual plot, it's also an indication that it is not linearly related. So this is me trying to bring our thoughts together. We also said that our line of fit can also help us to predict what our dependent variable is going to be. So even though you had scattered variables all around, our model, which has learned from all the values and picked the best line of fit, which is the result of our predicted values, which we can now use to be able to predict whatever new values of our independent variable that we have. We also said from your line of fit, you can be able to predict new values. For instance, if I have 7 and I trace up, at this point where I have about 7, it's telling me that my happiness index should be around 5.2, which was not originally available in data, as we saw before. Okay, so that's it for the line of fit. Our multiple R tells you about the correlation coefficient. The closer it is to 1, the more strongly related, positively strongly related your two variables are. The closer it is to -1 is the more negatively correlated it is. So the increase in one, of course, will mean a decrease in the other. And R squared value tells us about the accuracy of our model, that it is about 75% accurate, and accounts for a whole lot of variableness in the data. And also standard error. The smaller the standard error, it means the smaller our deviations are from the original value when predicted. All right, so we are going to hold on here. We are going to pause here. We are going to do other examples and other practices still on data analysis, but this would be the end of the video. Remember, your coefficients here are what we use to predict what our new values of independent variable should be. So once again, thank you for joining us. Please do well to like, subscribe, and we'll see you in the next video.